These are the notes for standard 3.4, which have to do with Newton's second law. And basically what Newton's second law allows us to do is relate the net force acting on an object, so the unbalanced forces, the mass of the object, and the acceleration of the object. And so this will allow us to either see how unbalanced the forces acting are on something and then calculate its acceleration, or if we know its acceleration, we can then calculate specific forces acting on the object. The equation that we're going to be using in the standard is F net equals mass times acceleration. So here we have a bucket that's being pulled upwards by a 40 Newton force. And so first what we're going to do is make a force diagram. And then we're going to calculate the forces acting on this bucket for both of these forces. So Fg is equal to mass times acceleration due to gravity. The mass of this bucket is 3 kilograms. Acceleration due to gravity is 9.8. And so we get that the Fg is equal to 29.4 newtons, and I'll put that near my force diagram. And then the tension force, they told us already, is 40 newtons. And so we can see based on these two numbers that the tension force is stronger than the gravitational force. And so I'll add those congruency marks to show that the tension force is stronger. And so what we need to figure out is how much stronger is the tension force, because that's equal to the net force. And so I can write down the net force is equal to the difference between the tension and the gravitational force. So that would be 10.6 newtons. And because the stronger force is upwards, then that means that our net force is also upwards. That's important because the direction of the net force is also the direction of the acceleration. And so, I give myself a little room down here. We can then use the new equation for this standard, which is F net equals mass times acceleration, in order to solve for the acceleration. Divide both sides by 3, and we get 10.6 divided by 3, 3.53 meters per second squared. And then the direction of this acceleration is up, because that's also the direction of the net force. So in this problem, we knew all the forces at the beginning, and then we used those forces to calculate a net force and to calculate an acceleration from that net force. For our second example here, we have a mover that's pushing a 13 kilogram crate to the left, causing it to accelerate at 0.6 meters per second squared across a surface that provides 4 newtons of friction force. So we've got the push on the crate from the mover, the friction on the crate from the floor, and then a normal force and a gravitational force. These are both vertical, and these will not be affecting the motion of the crate, since the crate is accelerating left. Part B asks us what amount of net force is acting on the crate. And so because we are given the mass of the crate and the acceleration of the crate, we can then figure out what the net force acting on the crate is. So the mass is 13 kilograms. The acceleration is 0.6 meters per second squared. And so we get a net force of 7.8 newtons. And because the mover is pushing to the left and it's accelerating to the left, then our net force is also to the left. So what that means is not that the force going to the left is 7.8 newtons, but it means that our left force has to be 7.8 newtons stronger than our right force. So we know that the normal force provided by the mover has to be equal to the friction force plus an additional 7.8 newtons, or an additional net force. And so we know that the friction is 4 newtons and the net force is 7.8. So we get that the mover must be pushing 11.8 newtons to the left, because if they're pushing that hard, that is 7.8 newtons harder than the friction is resisting them, and that will cause the crate to accelerate at the acceleration listed in the problem. So unlike the last problem, here we were given the acceleration in the problem. We used that acceleration to find the net force, and then that net force helped us to calculate the values of forces on our force diagram. Thank you for watching.